Hi, I am Dr. Abhishek Joshi, and in this video lecture I am going to discuss about the PIN and the APD photodetectors. So photodetectors we have introduced in my previous lecture that it is working as a transducer that is converting the light energy to the electrical signals, or you can say the conversion of photons to the electron hole pair. So we are having two types, that is PIN and the Avalanche photodiode. So in this lecture, we will be discussing three things, that is the PIN photodetector, APD photodetector and the detector response time. So let's start with the PIN photodetector. So PIN stands for the P-type layer, the intrinsic layer and the N-type layer. So these three layers we have, and the intrinsic layer width is very much higher than the P-type and the N-type. And we are applying the reverse bias voltage, that is the negative and the positive. Due to the application of the reverse bias, the working we have already discussed in my previous lecture. You can refer that. So we are having the load resistance, that is RL, and when the current flows, we are getting the current at the load. So here we can see the power level. So if we consider a power level, we can see that the power is decreasing from the width 0 to W, and here we are having the decrease in the power. The width of the intrinsic layer is from 0 to W. So this figure shows that the representation of an PIN photodiode circuit with an applied reverse bias. So an incident optical power level decays exponentially inside the device. So the device structure consists of a P-type and the N-type regions separated by a very lightly doped N-type or the N-doped intrinsic, that is I region. So in normal operation, and sufficiently large reverse bias voltage is applied across the device so that the intrinsic region is fully depleted of the carriers. So this is the basic working which we have already discussed. So when an incident photon have the energy greater than or equal to the band gap energy of the semiconductor material, the photon can give up its energy and excites an electron from the valence band to the conduction band. So this process generates the mobile electron and the hole pair. So these electron hole pair are known as the photocarriers, since they are the photons generated, that is the charge carriers that are available to produce a current flow when the bias voltage is applied across the device. So the photodetectors are designed such that the carriers are generated in the depletion region where most of the incident light is absorbed. So a high electric field present in the depletion region causes the carrier to separate and collect across the reverse bias junction. So this gives rise to a current flow in an external circuit, and this current is known as the photocurrent. So let's continue with this numericals and the derivation of the expression to calculate how much power will be absorbed by the photodetector. So at a lower wavelength end, the photo response cuts as a result of a very large values of AS. At a shorter wavelength, so in this case, the photons are absorbed very close to the photodetector surface, and the recombination time of the generated electron hole pair is very short, and the generated carriers thus recombine before they are collected by the photodetector circuitry. So if the depletion region has a width W, and given by the equation, the total power absorbed in the distance W is given by that how much power will be absorbed, that is given by PW. Integration from 0 to W alpha S P, that is the incident power on the photodetector, exponential of minus alpha S. Alpha is the absorption coefficient into the distance x, and d of x is nothing but the distance. Let's consider the distance. As we can see here, we have considered the distance that is along the x-axis varying from 0 to w, and w is nothing but the width of the photo detector. So the incident optical power that is given by P in 1 minus exponential minus alpha s, that is the absorption coefficient, into the W. So if you take into account the reflectivity, that whatever photons are striking the junction are not absorbed, it is somewhat reflected by the face of the photodetector. Now this reflection, the power reflected, is given by RF, that is the entrance phase of the photodiode, and then the primary photocurrent that is given by IP resulting from the power absorption. We can write it as, that is IP Q, that is charged by h nu, that is incident power, 1 minus exponential minus alpha into W, and 1 minus RF, that is reflectivity. So where power incident is the optical power incident on the photodetector, and Q is the electron charge, h nu is the photon energy. So two important characteristics of the photodetector are its quantum efficiency and its response speed. So these parameters depend on the material band gap, the operating wavelength, and the doping and the thickness of the PIN, that is p-type, intrinsic and n-type regions of the device. So the quantum efficiency eta is the number of the electron hole pair, that is a carrier pair, generated per incident photon of the energy h nu, and is given by, that is the efficiency is given by the number of the electron hole pair generated divided by the number of the incident photon, and it is given by the photocurrent, that is IP, by Q, that is charge of electron, divided by the incident power Pn divided by h nu, h where h is the Planck's constant, nu is the frequency. So here IP is the photocurrent generated by the steady state optical power Pn incident on the photodetector, and the performance of the photodiode is often characterized by the responsivity, and this is related to the quantum efficiency that is given by, that is R, that is given by IP. IP is the photocurrent, and the power incident, the incident optical power is Pn, and we know that we can have the eta q by h nu. So let's solve this numerical based on the formula. In a 100 nanosecond pulse, we are having the photons. So how many photons are there? That is 6 into 10 to the power 6 photons at a wavelength of 1300 nanometer falls on a indium gallium arsenide photodetector. So on an average, we are having the average number of electrons and hole pair which is generated, that is 5.4 into 10 to the power 6, that is electron and hole pair are generated. Let's find the quantum efficiency. So quantum efficiency, we know that it is given by number of electron hole pair generated, that is the output, and input is the incident photons divided by the number of the incident photon. So number of the incident photon is given by 6 into 10 to the power 6, and number of the electron hole pair generated is 5.4 into 10 to the power 6. Taking the ratio of these two, we are getting, that is the efficiency of 0.9% or 90%. So 0.9. So quantum efficiency at a wavelength of 1300 nanometer is 90%. So let's solve another numerical based on the reflectivity. So the photon of energy, so photon with the energy given by 1.53 into 10 to the power minus 19 joules are incident on a photodiode which has a responsivity of 0.65 amperes per watt. So if the optical power level is 10 microwatt, then from equation the photocurrent generated is given by IP, that is equals to the reflectivity into the power incident. So that is equals to 0.65 multiplied by 10 microwatts, that is given by 6.5 microampere. So this is the photocurrent generated by the photodiode, which is having the responsivity of 0.65. Now let's discuss about the Avalanche photodiode, also abbreviated as APD, Avalanche photodiode. So the Avalanche photodiode uses the Avalanche process to provide additional performance. The Avalanche photodiode possesses a similar structure to that of the PN or PIN photodiode, which we have discussed in the previous topic. So an Avalanche diode structure is similar to that of the Schottky photodiode. So the main difference of the Avalanche photodiode to the other form of the photodiode is that the operates under the high reverse bias condition, and this enables avalanche multiplication of the holes and electrons created by the photons or the light impact. So as the photon enters the depletion region and creates the hole electron pair, so we are generating the hole and the electron pair. So these charge carriers will be pulled by very high electric field away from one another. So in this high field region, that is the photo generated electrons and holes can gain enough energy so that they can ionize the bound electrons, and their velocity will increase to such an extent that they will collide the lattice, and this will increase to such an extent that when they collide with the lattice, they will create further hole and electron pair, and the process will repeat. So this carrier multiplication is known as impact ionization, and this newly created carriers are further accelerated by the high electric field. So thus gaining enough energy to cause further impact ionization. This phenomena is known as the avalanche effect. So the avalanche action enables the gain of the diode to be increased many times, providing a very much greater level of sensitivity. So as we can see in the figure, it is nothing but the stack of 4 layers, that is p-type, intrinsic, p-type and highly doped n-type. So a highly doped p-type and highly doped n-type, and it is intrinsic is sandwiched between these two. So as we can see the electric field distribution. So electric field distribution with respect to the distance x. So here with respect to the length, and this is the electric field distribution. So as the distance increases, the electric field increases. Now the electric field is maximum here in the junction. So here this is the avalanche region. Then again the electric field decreases and comes to its constant value. Then it goes to 0. So this is the minimum field required for the impact ionization or for the avalanche region. So this is the figure of reach-through avalanche photodiode structure and the electric field in the depletion and the multiplication region. So this is a common structure for achieving the carrier multiplication in RAPD, that is a reach-through avalanche photodiode APD. So when a low reverse bias voltage is applied, most of the potential drop is across PN plus junction, and this depletion layer widens with increasing reverse bias voltage until a certain voltage is reached, at which the peak electric field at the junction PN plus junction that needed to cause the avalanche breakdown. So the multiplication M, so multiplication factor we can calculate for the avalanche photodiode for all carriers generated in the photodiode is given by, that is capital M, and it is given by the multiplied output current, that is IM, divided by the primary unmultiplied photo current. So where IM is the average multiplied output current, IP is the primary unmultiplied photo current. So this is analogous to the PIN photodiode, and the performance of an APD, that is Avalanche photodiode, is characterized by its responsivity, that is RAPD, which is given by, that is APD reflective, that is responsivity, that is given by eta q by h nu into the multiplying factor, that is m. So, or we can write it is nothing but the responsivity with a unit gain responsivity multiplied by the multiplication, or we can see the Avalanche multiplication factor, capital M. So, where R is the unity gain responsivity. So, let's solve one numerical based on the Avalanche photodiode and the responsivity and the multiplication factor. So, given silicon Avalanche photodiode has a quantum efficiency of 65% at a wavelength of 900 nanometers. So, suppose we are having 0.5 micrometer of the optical power. So, this power is already given, that is known as the incident power or the input power, produces a multiplied photocurrent. So, multiplied photocurrent means PM is given to us, that is 10 microampere, or IM is given, that is 10 microampere. So, let's find the multiplication factor M. So, what we have to find? We have to find M. So, the primary photocurrent. So, for primary photocurrent, we know the formula. It is given by the responsivity multiplied by the incident power. It is equals to the internal quantum efficiency eta multiplied by Q by h nu and the incident power. So, we are having eta into Q into lambda. We have substituted the value of the frequency. It is given by C by lambda and SC and incident power. So, here we have the photocurrent which is generated by substituting the values. We are having the eta, that is efficiency is 65%, and the power, input power we have, then the multiplied power. So, substituting the values, we are having, we are getting the photocurrent as 0.235 microamperes, and the multiplication, we know that the formula for the multiplication factor is given by the multiplied current divided by the primary photocurrent. So, primary multiplied current is already given to us, that is 10 microamperes. So, 10 microamperes divided by, and the primary photocurrent we have calculated. So, that is 10 microamperes divided by 0.235 microamperes. So, we are getting a multiplication factor of 43. So, this is the primary photocurrent is multiplied by the factor of 43. So, these are the key points of the Avalanche photodiode. So, Avalanche photodiode requires a very high reverse bias for their operation. So, with this level of reverse bias, they will see the current gain effect of around 100 as a result of the Avalanche effect. So, Avalanche photodiode advantages, it required very high level of sensitivity as a result of the Avalanche gain. Avalanche photodiode disadvantages, much higher operating voltage as may be required. Avalanche photodiode produces a much higher level of noise than the PN photodiode. And the third one is the Avalanche process means that the output is not linear. So, the detector response time, for the detector response time, we can see that we are providing the reverse bias voltage. So, reverse bias voltage means the P side is supplied with negative and the N side is supplied with a positive. Now, due to this reverse bias, we are having the depletion region, and the electrons and hole pair are attracted by the opposite polarity. So, when we talk about the equivalent circuit model, here we can see we have the photodiode, the load resistance and the amplifier which is required. So, this is the equivalent current, equivalent circuit diagram. Here we have the photodiode excited with a photon energy with h nu, and the diffusion capacitance and the series resistance Rs and the load resistance RL and the amplifier resistance Ra and the capacitive effect due to the amplifier is Ca. So the three main factors that limit the speed of the response of the photodiode, they are the drift time carrier through the depletion region. The speed of the response of the photodiode is fundamentally limited by the time it takes the photogenerated carriers to drift across the depletion region, and that drift time can be calculated by the distance divided by the speed. So drift time is W by Vd. So diffusion time of the carrier generated outside the depletion region. The carrier diffusion is comparatively slow process where the time taken, that is T diffusion, for the carrier to diffuse a distance d may be written by, that is, the diffusion time equals to d square by 2 dc, where dc is the magnetic area diffusion coefficient. So the time constant incurred by the capacitance of a photodiode with its load, the reverse bias photodiode diode exhibits a voltage dependent capacitance caused by the variation in the shorted charge at the junction, and the junction capacitance Cj is given by, that is, epsilon naught A by D, that is a formula of the capacitance, and the capacitance of the photodiode Cd, that of the junction together with the capacitance of the leads and the packaging. So this capacitance must be minimized in order to reduce the RC time constant, which also limits the detector response time. As we can see here, we are having the percent of the total output. So here we are having the minimum value. As the time increases, the percent of the total output increases and it reaches to the response for the slow carrier. So this is the typical response of the photodiode that is not fully depleted. So ideally, to obtain the high quantum efficiency for a photodiode, the width of the depletion region must be greater than the reciprocal of the absorption coefficient for the material used to fabricate the detector, so that most of the light will be absorbed. Here we have transmitted the digital pulse, but if the width is very greater than the absorption coefficient, then we are getting this type of pattern which is required. But if the width is very greater than 1 by alpha naught with a large capacitance, due to the large capacitance we are getting the distorted pulse. So if we are having very small capacitance and width is very smaller than 1 by alpha naught, then again we are seeing the distorted tailing edge. So this detector response time, when the detector capacitance is larger, the speed of the response becomes limited to the RC time constant of the capacitance and the load resistance associated with the receiver current and the output pulse. And the device with very thin depletion layer has a tendency to exhibit the distinctive fast response and the slow response components to their output pulse, and may be observed from the figure C. So if RT is the total resistance combination of load and the amplifier input resistance, that is CT is the sum of the photodiode and the amplifier capacitance, then the detector behaves like the normal RC low pass filter. So we are having the bandwidth can be calculated as 1/2 pi RT into CT. So in this lecture we have discussed about the PIN photodetector. Then we have discussed about the Avalanche photodiode, APD or photodetectors, and the detector response time. So here I am going to stop this lecture. Thank you.